Hello everyone. Good afternoon. Welcome to Epsilon 2021. I am Vatsal Kore, MTT-S head of IEEE SIESGST.
And I am Tanisha Sheikh, WI Head at IEEE SIESGST. We are honored to be your host for this session. IEEE SIESGST's Epsilon 2021 is a brand new initiative with a prime focus on imparting technical knowledge revolving around our theme of computing and knowledge engineering.
We hope you all liked and learned a lot of new concepts from the first two sessions of the day, which were the introductory session on machine learning and cloud computing. And now, for the third seminar of the day, we have under the MTT-S track of our event an introductory session named Getting Started with Quantum Computing. In this seminar, our invited guest speaker will enlighten all of us about the basics of quantum computing and much more.
Let us now introduce you to our speaker for this session. We have with us Mr. Ramakrishna V, who is an IBM researcher and Quantum Associate Ambassador. He has a wide range of expertise and interests like mobile and ubiquitous computing, security, analytics, mobile commerce, service oriented computing, and cloud computing. He has more than 6 years of professional experience in both research and hands on software development. He is ever passionate about generating ideas and developing products and services to advance state of the art of computing technology. We are grateful and pleased beyond words to have him render his share of expertise and knowledge through this session.
So, without any further ado, let us invite Mr. Ramakrishna to the live stream to take over and address the participants present here for the introductory session on the emerging and extremely interesting technology of quantum computing.
Hello, can everyone hear me?
Yes,
Yes,
sir.
sir. Welcome,
All right,
sir.
great. I'm going to stop the camera while I'm presenting, okay? Let me just stop this and start sharing the screen. All right, can everyone see my screen?
No, sir, your StreamYard screen is visible. Yes, now we can see
Yes,
your
sir, we can
screen.
see it.
You can see it, right? All right, great. Okay. Right. How about now? You can see the full screen, right?
Yes, sir.
Yes, sir, we can.
Okay. Great, great. So, thanks for the introduction. I'm a senior researcher with IBM Research India in Bangalore and also a quantum ambassador. Can I ask anyone who's not talking to go on mute? Otherwise, I'm hearing a lot of background noise and also some echo. Thank you. Okay, so I'm going to be. This is a presentation about what quantum computing is at a basic level, and also what's been happening in the industry in the past few years, where we are heading, to a large extent from an IBM perspective. And I'm going to be switching to a different slide deck with some more basic information about quantum computing occasionally while I'm presenting this slide as well, this slide deck as well. So here's a rough outline of the talk. First, I'm going to talk about why we need quantum computing, why it's emerged as this radical new paradigm that everyone seems interested in, and what is it from a technical perspective. I'll give some examples of applications to which quantum computing already has been put to, and also range of applications that it shows immense promise for. I will then talk about IBM quantum computers, what IBM has been doing in this field for the past few years, and the roadmap that we are headed on. I'll then talk about what IBM calls the IBM Quantum Network, which is a worldwide group of it's a worldwide ecosystem of companies, academia, and IBM, which is going to enable knowledge sharing, and advancement in research in the quantum computing area. I will conclude this talk by talking about Qiskit, the programming framework that IBM has built and is offering for free, that allows pretty much any developer in the world to be able to program with quantum computing concepts and also on real IBM quantum computers. And at the end of the talk, I'll give a brief demonstration or a walkthrough of the IBM quantum experience, just to get all of you started on how to access IBM quantum computers and to be able to play with the tools and start writing some simple programs there. Okay. So without further ado, let me jump into the why and the what. Uh, did you know that about 1 to 2% of the entire energy of the world is used to create ammonia-based fertilizers? That sounds like an insane number, right? And in fact, it's 2 to 4% of natural gases in the world that are used to creating these. But ammonia-based fertilizers are, as many of you might know, quite crucial to agriculture all around the world. This is fertilizer are the reasons we've been able to scale up food production in the past few decades and centuries even. Uh, the the thing is, the energy consumption though is not really sustainable. Okay, neither in the agricultural field nor in industrial fields when we are thinking about petrochemicals. So how do we make these more sustainable? We need to figure out different ways or new ways of becoming more energy efficient, which means we need to be far more efficient about the technology that's used for all of this. The thing is, classical computers cannot do these because these are really hard problems. It turns out that classical computers are just, even the most powerful classical computers like supercomputers are too slow to solve these kinds of problems. And we can going beyond agriculture or industry, in the area of finance as well, to be able to do better predictions of risk. The today's computers, there are inherent limitations in what classical computers can do, and this is a problem with. Sorry, excuse me. Is there, just wondering, is there a problem with the presentation? Because I'm getting a call from someone. I hope it's not from you. Hello, can everybody hear me? Just want to confirm here.
Yes, sir, we can hear you, and the presentation is visible.
Okay, so it wasn't you who was calling me, right?
No, sir.
No,
Okay.
sir. You can continue.
Yeah, I just got afraid because someone called me and I was worried that it's one of you. Okay, sorry about that. All right. So there are these different problems that are quite intractable in the real world, and classical computers cannot really solve them. Moving on to issues like drug discovery, and as we've been in this world of the pandemic, as everybody knows, the past year. So figuring out new drugs for new kinds of diseases, again, it's another big challenge. So what's common to all of these is the fact that you have a problem space blow up in all of these classes of problems, which make them very hard or intractable for classical computers to solve. And here's where quantum computing offers a radical new paradigm. It promises to change what a trajectory that began just after World War II, when we had classical computers that started to solve to automate the solving of problems, which that technology did not exist before. Okay, so we to go from the application to theory, just take a look at this Venn diagram, and the white ellipse in the middle, that is the space of problems that classical computers today are good at solving. And we can, and that includes all classical computers up to ranging up to supercomputers. But there are a lot of other problems which are a superset of these problems that can be solved today. that are useful, and but that classical computers just cannot solve because it takes an exorbitant amount of time and memory to do that. That's really what the light blue ellipse indicates. So there's a lot of problems there that they cannot solve. Now the dark blue ellipse indicates the set of problems that quantum computing theoretically has actually been proven in some ways to be able to address. And this quantum computers show the potential to solve a lot more problems than can be addressed by quantum computers today. And not just that, you see this the dark blue ellipse going even to the right. It can also solve problems that we can't even think about or envision today. So that really is the transformational potential of quantum computing. So at this point, I'm going to quickly switch to a different slide deck to show you what exactly the potential is. Okay. So you all know polynomial functions, right? So this graph, what this shows you is, in general, when we think about computer programs, and I know many of you are probably in the beginning of a computer science education, but by and by, as you go on, if you do algorithms classes or you learn about computer complexity, these are going to be key concepts that you'll learn about. So the way we measure how fast a computer program works is usually through these kinds of mathematical functions. You can see here I've plotted three polynomial functions. One is a linear function, degree 1. Then there's degree n square, and n log n is can be approximated to a polynomial function with a degree somewhere between 1 and 2. Okay. You'll learn about n log n later in your career. Let's add a few more functions here. Now we're going beyond. Let's add n to the power 5, and then further 2 to the power n, 5 to the power n. Okay. Now 2 to the power n, 5 to the power n exponential functions, and you can see that even for a very small size of input, they basically shoot up. What that means is that the time and memory, which is indicated on the y-axis, is going to be exorbitant even if you have a slightly large increase in the load that or the input size that you provide to the program. I'm increasing the scale of the y-axis here. So now you can see we don't even notice the functions n and n log n. They're basically flat. N square is gone a bit to the right, increasing the scale even further. Now you see up to n square, we don't even see anything. N to the power 5 is still, it's growing, but we can clearly distinguish it from the exponential functions. If we increase the scale even further, now you can see all the polynomial functions are basically flat, which means that at fairly high input sizes, any polynomial function really is going to perform much better than even the smallest exponential function, even 2 to the power n, because you see 2 to the power n, 5 to the power n, both of them just shoot up, around the 43 mark here, as you can see here. This is on a log scale. The y-axis is on a log scale rather than a linear scale here, and you can see again the stark difference between polynomial functions and exponential functions. Polynomial functions essentially flatten out. What that means is that if you provide larger and larger loads, they're not going to consume an exorbitantly extra amount of time and memory, which basically means you can't solve them. What does that mean in real life? It means that for exponential functions, you can, if there is a problem that inherently is exponential, you can run a computer on it, but it'll run literally forever, like years, decades, and so on. And I'm not kidding. That's really what the challenge is with running exponential scale computer programs. Just to make this point a bit, to add a counterpoint to this, if we look at smaller sizes, as it turns out, polynomial can actually dominate exponential. So if we're talking about small input sizes, then this is the difference between polynomial and exponential is not that stark. As you can see, the n to the power 5 basically crosses over n square and n to the power 5 in this curves on this graph. But when you go to even if you increase the size of the input even a little more, we basically cannot handle exponential size state spaces with classical computers and classical computing programs. Okay, so I'm going to stop here and switch back to the earlier deck. Okay. So, sorry. So, how have classical computers been built over the past few decades? They've been built using on the basis of zeros and ones. Again, I'm not sure if any of you have this the background on how computers and logical circuits are built, but they are built on electronic circuits, which or other tiny switches, as well as which transistors can be used to emulate controllable switches, and then you can integrate a lot of transistors into an integrated circuit. And that's how, and by packing more and more transistors, we increase the computing power. But at its core, what it's based on is the ability of to be able to reason about any problem in the world using just zeros and ones, or bits, or binary digits, and our ability to build circuits to emulate those digits and do computation on those digits. That's how classical computers have been built the past few decades, and they've been able to scale. But this is still inherently limiting, and the future is not just zeros and ones. This is limiting because when we think about exponential size problems, then the state space is inherently going to blow up, as I just showed you. So what is quantum what does quantum computing bring to the table here? So you can see on the left, what we have in quantum computing is instead of bits, we have qubits, and a quantum computer, to expand it, a quantum bit. What a qubit is like a bit, which can have the value only 0 or 1. A qubit is also a unit of information in a quantum computing program, but it can have not just the value 0 and 1, but can also have be a superposition of 0 and 1 with certain factors. The factors of that you multiply the 0 and 1 state with, they are complex numbers. So this is actually the learning the math behind this, that itself is that's a lesson in itself. But for now, you can imagine we can have zeros and ones and a range of values in between. Okay, and those values can be tweaked using on a complex scale. Sorry. So a quantum circuit is essentially a representation of a program that you can build and run for a quantum computer. And a quantum circuit is a sequence of operations that can be engineered in hardware to transform a qubit state a qubit from one state to another. So you can see at the diagram on the right, what we have is we have 4 qubits that are being input, and then you have a number of these gates, these rectangles in pink, and they do some transformations, and finally you get something at the end. And what you see at the end here, this symbol denotes measurement. What's the key thing to note about measurement? It is that when you measure a qubit, the state of the qubit at that point collapses to either the 0 or the 1 state. And that means, in effect, that we lose the information about what it held, right? But the thing is that the probability of it collapsing to 0 is definite, and that is dependent on the superposition state of that qubit. So we know with what probability this will collapse to 0 or will collapse to 1. So in reality, what we would do when we're building quantum circuit is by running circuits multiple times, sufficiently large number of times, and we'll figure out based on our measurements of how many times we got a 0, how many times we got 1, we'll figure out the probability, and that will tell us, in effect, what state that qubit was in before we measured it. This really is the basis of all quantum computing. And at the end of the talk, I'll talk about a few more basics about how about some really basic quantum gates, and about the representation of qubits in mathematical terms, and so on. Okay, but that's at the end of this lecture. Why cannot we emulate what these qubits do with our existing classical computers? And this is a table that illustrates this really starkly. So one of the properties that so there are actually 3 properties of core properties of quantum mechanics that are being utilized in quantum computing. There is the superposition property, where we can have not just a 0 and 1 state, but anything in between. There's also the property that we can entangle two qubits, so that any changes we make to one qubit are automatically going to be reflected on the second qubit. And when we measure one qubit, and we measure two qubits, we will get the same measurement. So that's a unique property of quantum mechanics, and we can make use of that when we are building quantum circuits. Third property is interference, whereby we can, it's like if you're familiar with the physics properties of interference, where two waves can constructively or destructively interfere. We use that property as well in order to build circuits whereby we can engineer it in a way that it produces the right output we want by making different qubits interfere with each other. Taking one of those properties, the entanglement property, which is really key to making quantum computers as efficient to use in the real world. If you look at the table at the right, to represent the two entangled qubits, or the state for produced by two entangled qubits, you need 512 bits. That's fine. For 3, it's 1024 bits. But this keeps growing. When we get 35 qubits, to represent all entangled states of 35 qubits, we need 550 gigabytes. That's again sounds manageable. It's like some of our typical hard drives that we use these days. But then if you go to 160, this is more than all the atoms of planet Earth. Okay, this is really exponential growth, which is, in the past year we've been hearing about exponential growth in the context of COVID, but you can imagine it here as well. And then when you go to 280, the number of entangled states is more than all the atoms of the universe. So basically, this is impossible. When you get to 160 or 280 qubits, it's not just about the difficulty of doing that on a classical computing. It's now we have reached impossibility stage. Okay. And okay, I'm going to quickly stop there and see if there are any questions. So I can't see what's happening because I'm just projecting the whole screen. So if the moderators want to ask any questions, yeah, go ahead.
Yes, sir, you can continue. We will take the Q&A session at the end.
All right, sure, sounds good. So now I'm going to quickly talk about the applications that quantum computing has been used for and also has the potential to be used for. Okay, before I go into the technology that's behind quantum computers. So, very broadly speaking, quantum applications span 3 areas. So, surprise, they can be used for simulating quantum systems, as you can see at the left. What does that mean? As you might know, if you've been through high school history or chemistry, physics or chemistry classes, then you know that quantum mechanics or figuring out the quantum dynamics of atoms and molecules can get really complex when you go from a small atom to a large atom or a very complex molecule, and it's an exponential size increase in the state space, and it's going to be very hard, very challenging to do this computation, and it is for a classical computer. So broadly speaking, simulating these kinds of quantum systems is something that quantum computers can and are used primarily for. And applications lie in the area of chemistry, material science, as well as high energy physics. The second broad category is AI. So the past few years, you've seen an explosion or an acceleration in AI technologies as well as their adoption in the real world. But that's nothing compared to what we can expect once we have quantum computing. We can get far better and faster pattern and feature recognitions, and these tend to be beyond the capabilities of today's classical computers. Even though there's a lot of work has gone the past few years to build good models. Similarly, in the machine learning area, we can train models much faster and get a lot more accuracy very quickly with quantum computers. Lastly, optimization is something whereby we are trying to figure out what an optimal solution is from a literally an exponential number of potential possibilities. And one of the applications or rather one of the algorithms that has been used for classical optimization with the Monte Carlo simulation. What we have produced in the past few years, and there was a partnership between IBM and a financial company that actually made a significant advance in doing Monte Carlo simulations. It was a real advance in the sense that no classical computer can do it as fast as they were able to show a quantum computer could do. What can these optimizations be used for? You can do this the various financial applications. There's if you have if you want to optimize your investor portfolio. Uh, Big banks and governments would like to keep doing risk analysis as well as try to monitor any nefarious activities that are going on in the economy, loans, this scoring of people's credits, and so on. Okay. Uh, this is actually a flagship example where uh, IBM and a partner. This is the Daimler car company. They produced some significant advances with the help of IBM's quantum computers and the technology that we brought. So. Daimler, like many car companies, they are trying to transition to the new era where you would like to build more energy efficient batteries. And we also need to do this at a very low cost. The batteries need to be high capacity, and they need to power the next generation of electric cars. The thing is, existing technology does not necessarily have the provide all the good properties, but also figuring out how to build these batteries, which is often involves a lot of trial and error and lots of simulations, can be quite interactable in classical computers. So, for example, one of the things that you want to do is figure out how to model a lithium sulfur battery, because this had some promise to be a lot more energy efficient than existing lithium ion batteries. So using quantum computers and quantum computing algorithms, Daimler and IBM in partnership managed to do this in a way that showed that is they were able to model lithium sulfur, and and we were able to produce advances that gave new insights into how that would work, and thereby made a big advance towards producing these energy efficient and fast charging batteries. Just for a flavor of what this involved, this is like a very zoomed out version of a circuit, the quantum circuits with a lot of quantum gates that was used to run this program that produced the output that was desired. Okay. So I alluded to the financial optimization problems. So this was the where a fundamental advance was made to a Monte Carlo-like sampling algorithm, whereby JP Morgan Chase, one of the biggest banks in the world, was able to researchers there and in IBM were able to figure out how to do optimizations a lot faster. So the we mentioned the quadratic speed up. What that means is that if you think of I showed you the functions earlier on, if you can do something in linear time in time that is of order n, we were able to do this in order root over n, which is as the size of n grows, the time taken to solve a particular problem is a lot less with the quantum computers than with classical computers. And again, the program or the circuit that was used for this is presented here in a zoomed out way. The last example I'll talk about is trying to measure or calculate thermodynamic variables. And IBM, in partnership with ExxonMobil, one of the biggest oil companies in the world, demonstrated advances whereby we can use quantum computers to accurately calculate these variables. And again, the impact of this is that we can start figuring out how to build technology that is a lot more energy efficient and can also produce clean and affordable energy. So the common thing to this problem, as well as the problem about cars, is like if you think about trying to what we need to do is to be able to model the states of uh, uh, a particular molecule. So if you think of just an atom, you have a number of electrons. And the hydrogen atom is one electron, but then you go on to bigger atoms. They, you have 20. Let's say you have an atom with 20 electrons or such. The the way all those electrons interact with each other produces an exponential size expansion in state space, and that's just maybe we can model hydrogen and helium efficiently, but when you go to larger atoms and especially molecules involving multiple atoms of different elements, it's going to get very hard. But with quantum computers, we have made some advances in this area by being able to model these the energy states of these atoms and molecules, even somewhat large ones, efficiently in a way that classical computers just cannot do. Just pause for questions here. Okay. So take a look at this diagram. So what we have juxtaposed here is a picture from 1944 to a picture from 2019, and this is really what it looks like even today in early 2021. What do we have in 1944? This is a picture of a computer that was built in Bletchley Park in the UK. So if you know the history of this is the area where Alan Turing and others developed the codes to crack the Enigma machine, the German Enigma machine. But this is also where was one of the early pioneering centers of computer building. And these machines, just like their counterparts that are built in the US, which names you may have heard of, like the Mark II or the ENIAC and whatever followed that, all of those were housed in these big rooms. Today we have computers we carry around in our pockets, but in the beginning you had these humongous machines that were housed in big rooms, and also to be able to do anything useful with them, you had to physically go there and do some programming, as you can see these ladies doing there. When you look at this picture at the right, it seems somewhat similar. This is actually what a quantum computer looks like. This is in the IBM New York Research Lab. What is the difference between the two, though? The similarities are clear. You need big rooms, and you need people to go there to do anything related to making any changes to the hardware. But this computer, unlike this one, can be accessed by anyone, including all of you, from anywhere around the world, from your laptops. And that is made possible because of the communication advancements we made in the past few decades, and the fact that we have clouds that allow access by a lot of different people simultaneously to be able to do things on these computers that you otherwise would not be able to do. So in effect, you or I, we can all, each of us, be simultaneously programming on a quantum computer like this, which is sitting in New York. We would not have been able to do that back in 1944. Okay, so the point I would like to make here is that despite the fact that we are in the early stages of quantum computing, where we still need to house these computers that are huge in rooms of their own, we don't have like laptop-sized quantum computers today. We can actually exercise them in a way with an ease that was just not possible in earlier era. And that allows us to both gain knowledge as well as advanced knowledge in a way that's much faster than people were able to do in the early era of quantum computing. So now let's look at this is the interesting part. So let's look into what exactly lies within an IBM quantum chip. Okay, just like in a classical computing chip, where you have a microprocessor, you have buses, you may have memory units, and so on. This shows you exactly what lies in a quantum chip at some level of granularity. So the resonator is really it's like a communication line. What this does is what each quantum chip has, in effect, are multiple qubits. By qubits, I mean there's some technology here that has the ability to produce qubit states that are in superpositions of zeros and ones. Okay, and that technology is in IBM quantum computers. The technology that's used is superconductors, or what you call superconducting transmon qubits. What this is that there are plates of aluminum and niobium that are like arranged like a capacitor, and then we have the ability to move an electron through them, and the electron can then go from a ground state, that is zero, to a superposition, that is in a state that can be in equal probability of 0 and 1. So once we get a state in a superposition, then we can do computation using other quantum gates and build arbitrarily complex quantum circuits with that. So the takeaway you should get from this is that there is the qubit technology that's used here are superconducting qubits, and we can have multiple qubits on a particular processor, and they are arranged in a kind of a lattice configuration. That is, think of any sort of graph. If you think of four qubits, you can think of them arranged in a rectangle. But you can arrange them in various different shapes, and there are reasons to arrange them in particular shapes for efficiency purposes. We won't go into that right now. But the connection between the qubits is what is referred to as a resonator. And when you want to read out, that is, I mentioned that qubits can be measured and need to be measured at the end, right? When they to figure out what the state is. So the readout resonator is for the measurement line. So there are, just for reference, I'll mention that there are other technologies for building qubits. There are technologies that are called ion traps or trapped ion. There are semiconductor-based technologies. There's something called topological qubits. There are also people are trying to build qubits using photons, and photons are really the classic quantum particles that is exhibiting quantum effects, as well as the wave particle duality. But not all of these technologies are having as much success, and at this point, at IBM, we are very confident of. We have a lot of expertise in superconducting qubits. We've made a lot of advances in the past few years, and this looks like the technology that can scale a lot. The other point I want to mention is to be able to build these superconducting qubits, you need to cool this the thing here to very, very low level. It's in this case to about 15 millikelvin. Okay, that's very close to absolute zero. And yeah, in our quantum computers, you actually have qubits that are at 15 millikelvin, and so they have to be. That's the reason they have to be protected right now. And maybe in the future we'll see some advances whereby you may not need to do that. But for now, this is how we do it. And the superconducting qubits are also have been shown to promise very high speeds compared to other various competing technologies. This is a both a bit of history as well as the future projections of where IBM quantum computing technology is headed. So IBM's first quantum processor was actually built not in 2019 but in 2012 with a single qubit. Then 2016 we built a 5-qubit machine that was then offered on the cloud. So in 2016 was the first time when an IBM quantum computer or quantum processor was built that was to which everyone in the world was given access to via the IBM cloud. Fast forward to 2019, this is the flagship Falcon processor, which contains 27 qubits, and this is important for another reason I'll mention in a couple more slides later. Then last year we also produced the 65-qubit machine called the Hummingbird, and this year we're going to produce 127 qubits. The increase, the numbers seem somewhat random just because, as I mentioned, you're going to have qubits arranged in different configurations, and the configuration determines what the precise number of qubits is going to be. Okay, so that's a level of detail that we don't have to go into right now. The way we are able to increase, or the reason to increase the number of qubits first, is because we would like to build computers that can do more and more, as well as solve a larger variety of problems. So actually, we need computers with more and more qubits, just like we pack more and more transistors into a classical computer, thereby making them much faster and more efficient. Okay, but it's not always just about increasing the number of qubits. The thing is, if we look at the state of art today, qubits are can be quite unstable. So there's a lot of work and a lot of research going on in how to build quantum computers that are with minimal amount of errors. Because the qubit states, if they are not going to survive for very long, then it's very hard to get any user computation out of them. So there's a lot of work in making these minimizing the errors or making them error free, and also there are a lot of other technologies like doing proper packaging of the hardware, which can contribute to giving us better performance. So there's a lot of different factors that go into this. Uh, One of the things that so there's some concepts that you should keep in mind. There's something called a quantum advantage, whereby a computer. What do you mean by quantum advantage is that it's a stage when we'll be able to solve problems using quantum computer that's much faster than how any classical computer in the world can do. We have not quite reached that stage yet. We are getting there with certain types of problems, but that's the goal or the practical goal for any quantum computer. So we can do that both by increasing the number of qubits as well as by reducing the errors. By there's a lot of software improvements you can make. There's packaging improvements, so on. From 2023 onwards, our goal is to build much larger scale quantum processors with more than 1,000 qubits. That's target for 2023. And further on, just like in classical computers, when we went beyond a single processor machine to you have a multiprocessor, a multi-core machine, as well as multi-computers and GPUs and so on, which are really group of computers that can efficiently be corralled for any problem. So that's what these stacks show here. These are like stacks of quantum processors, and that's the way we can scale, and we envision scaling to even up to million qubits and beyond. This is what our IBM quantum system looks like at this point. So you may have seen this picture. So we'll go through this animation quickly. And here, what you have in this structure is at some place have this is like a prototype that we have in the Yorktown Research Lab in New York. This is what we call a super fridge, and I showed you the stackable computers or stackable quantum processors that can be used to house a million qubit machines. So that's what we are the process of building here, and this technology can house these stackable quantum processors here in these big chambers. So called super fridge because we have to keep them at very low temperatures in order for the qubits to be able to function as the process requires them to. So this is another concept called Moore's law, which some of you may have heard of, or if not, you will during your computer science career. Classical computers, the ability to pack more and more transistors every year into integrated circuits has been the basis for the entire computing revolution over the past 50 years or so. So Moore's law predicted that the computing power was going to keep doubling roughly 1.5 years. I think that was the projection, and as it turns out, it has. The Gordon Moore, who was one of the founders of Intel, made this projection, and we have actually been following Moore's law for the past half a century. We can actually do some kind of similar projection for quantum computers. So to be able to do that, we need a measure, and quantum volume is a measure that has been created. It's actually created in IBM, and is being used by various researchers in the field to measure or estimate how well a quantum processor can do. And a quantum volume is not just about how many qubits your processor has. It's also about how error-free that is, how long a qubit state can be maintained. That's what's called gate fidelities. That's this concept called coherence time, which is yeah, how long a particular superposition state can be maintained for a given qubit. But we can derive a measure that tells us whether or not our a particular quantum computer with a certain number of qubits and a particular and built with a certain kind of technology, what exactly is its processing capacity? That is, what is it good for? How many how many programs can it handle and give us correct outputs? Uh, so that has been increasing roughly in the same way that over the past few years. And as you can see, we have a graph from 2017 onwards, just the way Moore's law has. So we envision that we can use the quantum volume as a metric to track the progress of quantum computers in the present and well into the future. And in fact, the curve may actually not be linear, but maybe even faster. In the past year, a quantum processor that IBM built, Falcon, that's a 27-bit quantum machine. It researchers were able to increase its quantum volume to 64, and then further, just within a few months, increase it further to 128, and all purely through software improvements. So these are really exciting times. We are not quite at the place where quantum computers are clearly going to be superior to classical computers in a lot of different ways, but we are on that way, and there is real progress that we can track over the months and the years. Okay, briefly pause here again for questions if any of you may have it.
No, sir, you can continue. We will take all the questions at the end.
All right, sure. Sorry, I keep forgetting that. All right. Yeah, sorry. So what you see here is a bird's eye view of how we envision quantum computers are going to be used today. In fact, they are being used today in this way. What you have at the left here, these are quantum developers like you and me. We have our laptops. We would like to be able to program on a quantum computer, but really we're not going to go to the room that houses a quantum computer. We're going to be trying to program from our laptops, and what interfaces us or intermediates us from the quantum systems is the cloud. In this case, we're talking about IBM systems, so there's IBM cloud. So what happens here is we program something, we send the program via the IBM cloud to the quantum system. The quantum system then does the processing, returns it back to us via the cloud. Okay, let me just run a quick animation that shows you what's going on here. You write this program here, as you see, send it to the cloud. The cloud does what we call a transpilation, which means it converts that program into these circuits. And these circuits are sent now in the form of microwave pulses into these quantum computers. Processing is done, measurement is done, it sends it back through the cloud back to our laptop, and on laptop we can see the output that we desire. Okay, that is a very bird's eye view of how exactly we envision this working. So what you can see here is that we don't just have quantum computers, or rather, we are not envisioning quantum computers replacing classical computing. What you're talking about is quantum computers complementing and augmenting the capabilities of the classical computers that we already have. Okay, so there's going to be the symbiotic relationship between classical and quantum computers for a while. It's not going to be just quantum computers. Okay, so a lot of anyone who's classical computing programmer, your skills are going to be used and going to remain valuable for a long time. In fact, the ability to program quantum computers relies on similar programming abilities to what you've already learned in classical computing. Okay. Yeah. So, sorry. So this is, if you look at the what's written at the bottom, This is where we are trying to head towards. So what this means is that if you look at this program above, and again, I don't know how many of you have programming abilities or programming knowledge at this point, but this is a very simple Python program, and usually you don't have four-line Python programs. Generally, to solve any kind of non-trivial problems, you may need to write hundreds of lines, but what we want to get towards is for people who want to be able to solve problems using a quantum computer in order to get their outputs much faster than they could using a classical computer. We do not want them to be able to have to learn some very complex tools, or go get a graduate degree in physics to be able to understand how to program on these. Anyone with a maybe a minimal programming knowledge, but who has very good knowledge of their particular domains, like the car companies. People in the car companies may have good knowledge about what they wish from their batteries. People in financial companies or banks may know exactly what they want from their portfolio management tools. They should be able to just specify their problem in the form of using a data file. Provide data file to a four-line program like this and say, okay, run this on a common computer, give me the output. We want this to go to that level. So we want people to be able to use quantum computers without needing to understand at the core what the quantum technology is. Okay. So uh, what is the what do we need for quantum computers to actually be relevant to industry? Just like in classical computers, we the way we've been able to use classical computers in a variety of different problems and industries in the real world is by improving their quality first of all. So you cannot have if a computers were highly error prone, then there would be no point in using them. So in classical computers, there's been a lot of effort that's gone towards first making individual processes be very accurate, as well as add a lot of fault tolerance mechanisms so that if there are any faulty parts, then we can use some good and highly performing software to be able to paper over those faults. So quality is something that we have in the classical computing. We want to bring that in the quantum computing world as well. And this what this means is we need to be able to reduce operation errors, reduce qubit errors, make sure that the qubits stay in the states for much longer, and thereby we can build much larger quantum circuits, and we can keep tracking their quantum volumes to make sure that we are actually making progress. Capacity means like in classical computing, you can the more the computers have the ability to run multiple programs at a time simultaneously. So the more you can run simultaneously, the more people you can serve within a given amount of time. So quantum computers, again, we given our technology that is built on the superconducting transmon qubits, as well as a lot of quantum computers that we have built and deployed for use through the cloud. And I'll show you some numbers later on. You can run a lot of programs. So people all over the world, in fact, can and do run a lot of programs, or what we call in this parlance quantum circuits, simultaneously on IBM quantum computers. And this is something that we want to maintain and keep increasing. Lastly, we would like to be able to make sure that anyone who has that domain knowledge and who knows what they need, they have the flexibility to be able to build circuits that can utilize the best features of both quantum computers and classical computers, and build the right kind of algorithms for the problems. So that gives a variety to the kinds of algorithms that our systems ought to be able to support, and also be able to, these systems then can solve a much larger class problems, and they can handle applications that basically range all of the problems that we have on earth here, like I talked about earlier on, from agriculture to industry to finance to medicine. uh, this is a road development roadmap that we have, and I showed you the processes earlier on. That's here at bottom from the 27 qubit processor we had in 2019 and to our goal of scaling beyond to 1 million qubits somewhere in the latter part of this decade. Uh, let's first look at the stack. So, if you again, if you become a professional software developer, you'll understand the software. Any software is built in a layered manner. You have a tech stack. You have some software that's built at the bottom layer that is very close to the hardware that people with deep hardware knowledge are going to build. Then just above that, you're going to have software that's built assuming that the hardware, the people who build those hardware routines have done a good job and that they can rely on them. So there are so it's like at every higher level, people depend on the programs and the subroutines that have been built by people at a layer below them. What are these layers here? So just above the quantum systems, you have we envision three classes of developers. There's a kernel developers are people who actually build quantum circuits, who understand how quantum hardware works, and who know how to get maximum performance out of a quantum computer. So they know for a given small problem, what would be the right circuit to build for that. And they can also use various other technologies that we're building right now, including Qiskit runtime. Qiskit is a programming framework that I'll talk about. The ability to create dynamic circuits, which is a mix of both quantum computer circuits as well as classical computing mechanisms, uh, various libraries as well as some control systems. We're not going to the details of this for now. Just keep in mind that all of this at this layer requires some a good knowledge of how the processes work, how quantum computing works at very low levels, and those are people we envision being the kernel developers. There's another class of developers or algorithm developers who are going to be relying on these the software that's built by these kernel developers to be able to create routines in that can be used not for one particular area but for various different areas, like from the natural sciences like chemistry and physics to finance to optimization to machine learning. And finally, you have what you call model developers. They are really, you can think of them as domain specific application developers who are going to be relying on these subroutines. Again, they at this point we are very far from the hardware. In order to be able to build particular applications in that particular areas, like for example, the people who are trying to model the lithium sulfur battery in time. So at this point, up to 2022, we have all of our early adopters here. 2023 onwards, we envision that people are going. What do you mean by early adopters? Are people who have um, uh, who have decided to partner with quantum and use quantum computing technology without it actually being necessarily ready for prime time. But beyond that, we envision that once quantum computers mature, the error rates get very low, then we're going to see a lot of lot more of these, especially these model developers who are going to be relying on code that was already written in the past. Looking at these developers again, in the classical computing history, what originally happened was you had people who were writing again code that was very close to the hardware. So in the early years and decades of computing, you would have a lot of people who had to be assembly programmers or machine programmers who would have to write code in languages that were tied very close to the hardware. Then you had when computers sort of started getting standardized, the instruction sets started getting standardized. You had the ability to create or compiler technology got much better. We had the ability to create higher level languages like going from from C up to today Java, JavaScript, and so on, which people who do not know anything about the computer hardware can actually program fairly easily on and do something useful out of it. So in the early decades of classical computing, you had a lot of kernel developers, few application developers. So it was like you can think of it as a pyramid where you have At the base, you have kernel developers, lots of them, and few model developers. Just like in classical computing, in quantum computing, that is mostly the case now. But we want to go to a place where the pyramid gets inverted. So at a point where you need very few kernel developers or specialists in hardware programming who can create advanced control systems or circuits that are highly performant, and instead you're going to have lots more application programmers who are going to be writing on the basis of those subroutines. So that, I hope, gives a high level overview of where we envision us headed. So the key takeaways here are three. One, we are building a Qiskit runtime. That's a programming framework and a runtime that can run quantum applications 100 times faster on the IBM cloud than we have recently been providing. So we are going to be relying on hybrid cloud technologies that IBM has been a pioneer in and one of the leaders in at this time. And we're going to be using both hybrid cloud technologies as well as advances in quantum computing to make this a lot faster. We're going to be using concept called dynamic circuits that will be introduced both classical computing as well as quantum computing paradigms, and thereby improve accuracy and reduce the amount of resources required. And by reducing resources, we also end up increasing the capacity of the systems to run more programs at the same time. And finally, we're going to be creating a lot of application modules that are going to be used for a lot of different applications, are going to be used and reused for a lot of different applications. So moving from here to the IBM Quantum Network. So IBM Quantum, the thing about quantum computing is that it's still a growing technology, and even though it's not like one person or one organization can produce all the advances. So there's a lot of collaboration that's going to be involved in this process. It's the IBM can provide the hardware and programming frameworks, but then we need to partner with people who are in the real world, who know what are the problems that are important to solve in their areas, who can partner with us, and thereby produce advances in solutions, as well as in the process produce advance in the basic systems that can then feed back into improving the quality of the quantum computers themselves. So our goal for IBM has, since 2016, when we first exposed quantum computers to the cloud, was threefold. We want to be able to educate and train a workforce that understands how to program on quantum computers, and we also want to partner with researchers and around the world who are interested in this area and who understand what a game changers can be. And finally, we want to partner with industry experts to be able to develop applications. And all of this, there's a nice feedback loop here. The more people we educate and train, the more they'll be able to invent new things in terms of both core research as well as in applications. And that will then improve the quality of quantum computers, and then we can do more with those quantum computers again. So the quantum network is really a collaborative process of discovery, whereby we can arrive at a place where quantum computers can gain significant advantage and perhaps supremacy over classical computers. Uh, so Yeah. So I just mentioned this sort of feedback loop whereby IBM provides the technology and to solution developers. Solution developers can then use that technology, including that consists of our quantum computers as well as our programming frameworks, and then figure out how to solve a problem that a classical computer cannot, and that gives us more new insights that we can then feed back into improving the quality of our quantum computers. So I mentioned the algorithm families here roughly align with the classes of applications I mentioned earlier. Quantum simulation is can be used in for quantum mechanical modeling in physics and chemistry. Linear system refers to problems in AI for better pattern recognition, and quantum walks is one of the techniques used for optimization. Um, I also talked about application developers and different kinds of the layers of developers, from kernel developers to people who write algorithms that are not tied to a particular application, but then above that you have application developers who want to solve a particular problem in a particular area. You can see a list of different applications that these can be, that quantum computers already showing the potential for. So one example I'll take is logistics and routing optimization. So if you are aware of this program called of a problem called the traveling salesman problem, it's an algorithm whereby you need to find out, again talking in plain English. You have a salesperson who would like to cover different cities in order to sell a product and come back to the original city. Now there are different ways of or there are different combinations in which he can go. He can go, if you have 10 cities, he can go from city 1 to city 3 and then to city 5 and so on. The trajectory is up to him, but what he would like to do is to minimize the total distance that he's covering in this entire process. It turns out when you go to very large number of cities, then this problem gets very, very hard for classical computers to solve. And this is one of those intractable problems. If you remember the Venn diagram I showed in the early part, this does not lie in the central white area. This lies in the blue area. Problems that whose state space just blows up in an exponential way, and therefore they need something else besides the computers that we have today to solve them. And quantum computers show strong potential to solve those kind of problems. So, to talk about how we can solve those kinds of problems in using our quantum network, here's an example. So, a few years ago, IBM quantum researchers published a paper on amplitude estimation. It's we don't have to understand what that means. It's one of the quantum computing concepts. And what happened to it then was the researchers in Keio University in Japan took that method. They read the paper, they advanced the method that was in the paper, and then they published along with companies, Mizuho and MUFG, which is a bank. And then the results of these were then discovered by JP Morgan Chase, another big American bank, and that method was applied to for option pricing and for publishers, which is some of the things that they JPMC and other banks want to be able to do very efficiently. And finally, when they solved this problem, they were able to contribute the solution, whether in the form of library functions, to the Qiskit programming framework, which is Qiskit is a programming framework that IBM has released as an open source programming framework, as well as open access, and you can write Qiskit programs on top of IBM quantum computers. So you can see here the loop that happened. Research originated in IBM research. It underwent some borrowing up to the point where it could solve problems, and then finally, when a solution was found, then it was fed back into this open source framework, which can then be used not just by IBM but anyone around the world. If you go and you play with the Qiskit, you want to program with it, you'll be able to use the routines that are built here. This is a snapshot of what the IBM quantum network looks like. So we have 140 members worldwide, and what we have here is a mixture of different kinds of entities. We have universities, we have big businesses, but we also have small startups and various kinds of industries and organizations represented here. So also the range of interests here is quite wide. There are people with who have pure research goals, up to people who have purely to people who just want to solve a problem, and then there are people who just want to learn and they learn or to impart that education. So the research, application, educational goals, a wide variety of interests. And our hope is that this network again is going to keep expanding. The bigger these networks become, the faster research gets. And generally, that's been something that we have discovered over the past decades and centuries when it comes to any kind of scientific endeavor. Um, Also, the other advantage of being part of this network, as opposed to not being part of this network, is that you very quickly you can find out what others have been doing in this network. You can use the research output and as well as the programming output of other people who are participating in the network much quicker than you would if you were not within this. Uh, okay. Sorry, my I just skipped a couple of slides. So these are different kinds of partnership structures we offer. One of them is like we can build some hubs, and the difference between all of these is in scale. So a hub is really has big ambitions. It's like we IBM goes and deploys a computer in a particular area, and that can then be a quantum computer, which can then be used and augmented by various stakeholders, including universities, big industries, maybe even governments in that area. And I'll show a couple of examples later. Then we have somewhat smaller scale collaboration with industry, where we can partner with particular companies, share know-how, and then help them solve their problems, and then in the process, then use whatever output came out of that to advance the research in other areas as well. And finally, we have ecosystems which can be limited to imparting education and training. That's what the diagram at the right indicates. Uh, so the quantum network at a snapshot looks like this, and the numbers are quite impressive as you can see. So what we have are at this point about 300,000 users have actually built and run quantum circuits on IBM quantum computers. That's a total of 700 billion quantum circuits since the time IBM released its quantum computers for access on IBM Cloud. Today, we have an average of 1.4 billion quantum circuits that are being deployed and run on IBM systems. We have a total of about 34 quantum computers that are deployed and that are accessible, but of these, all of them may not be online at any given time. Some of them you have to bring them down for maintenance occasionally, but most of them are. Already mentioned, we have 140 clients and partners in the Q network, and collaborating on more than 30 applications. Also, the Qiskit framework, which is this programming framework that's both open source as well as open for access, has about 300 contributors worldwide at this point, and it is one of the most widely used quantum computing frameworks. From a researcher's perspective, we published about there are about 400 scientific papers published by people who have utilized IBM quantum computers, and of these, there are at least half of them are involve collaboration between IBM researchers and people in academia and industry. And this is just a snapshot of just some a selected set of papers that we have been publishing, and the main theme or the most prominent themes you see represented here are in chemistry, finance, optimization, and machine learning. The how we can go about building quantum hub, that's we what we can do is there are actually different levels of engagement that IBM offers. There's from free up to variety of paid engagements, and the thing is, the higher up we go, that's the higher levels of pay you get more and more powerful quantum computers to work on, as well as more technical know-how that you may not get directly from the free tier. But what we do is we offer quantum system access. If you see the resources that we offer, the systems can be accessed via the IBM Cloud. We offer support and enablement, and the programming framework is part of that. And as well as we can partner with companies in academia for collaborations and different tracks. We can solve the problems for industry. We can partner with academics for skill up people, and we can also partner with the researchers to drive the state of the art forward. Um, this just shows this is a Google Maps bird's eye view of a couple of quantum computers. This is in a New York facility, and we have 34 computers that I mentioned earlier, spanning between 5 and 65 qubits. Usually, the computers with the higher number of qubits are not open for access to everyone, but whatever you can get access to them with a paid engagement. But yeah, usually we are in partnerships with the universities and companies for that. At any given time, you likely to have about more than 95% of these computers available for users. So, lastly, I'm going to talk about Qiskit. So, the Qiskit is a programming framework that allows anyone, you or me, to program on a quantum computer. All we need is knowledge of basic Python programming. And IBM is the only company really to offer both real quantum computers as well as this kind of an open source and completely openly accessible framework for programming on these computers. So, as I mentioned earlier, we have different categories or different tiers. There are some computers offered freely for the public, and then we also offer premium access by the cloud. And our Qiskit framework, which is a Python-based framework, is open source, and anyone can use it, or if you learn enough, contribute to it as well. And finally, the reason for doing all of this is so we can educate people like you all, as well as or whoever else is interested in quantum computing, to be able to get ready to program on quantum computers in the near future, because we are heading towards a point where quantum computers will be used in the real world to solve problems. And as I mentioned, the roadmap, we have a plan to go there. But to be able to exercise that capability, we need a workforce that is skilled in quantum computing, in quantum computing as well as in quantum programming technology. So that's why we want to build this worldwide workforce that can both benefit us as well as themselves and various other people around the world, in order to make quantum computing a success and solve the world's problems. Uh, as part of Qiskit, so what do you get in Qiskit? You can actually go to qiskit.org, and under that you have a textbook, and this is a free textbook that any of you can go and read, and you learn the basics, the mathematical foundations on which quantum computing is built, and onto that is linear algebra primarily, and then you learn some basic quantum algorithms, and you learn a lot of different programming skills. As I mentioned, you just need to know basic Python programming to be able to start programming in Qiskit. Finally, this is just a snapshot of a couple of hubs that IBM created in partnership with governments. One is in Germany, and another is in Japan. So, yep, that's it at this time. I'll just briefly stop for questions before I go to the demonstration. Or should I just jump to the demonstration? Moderators?
You can go with the demonstration, sir. At the end, we will take all the questions.
All right. Just before going to the demonstration, I will quickly just present a couple of slides that show what okay. So just to compare classical quantum computing with classical computing, in classical computing, we have bits, zeros and ones, and they are our primary states. So any state in classical computing, so any kind of programming you do, essentially building on zeros and ones. Qubits in quantum computing are not just zeros and ones. You can think of them as states or unit vectors And you can see these are also can be also be represented as column matrices, and that's where linear algebra comes in. By the way, if you to understand quantum computing and at its core, and to be able to reason about how to build quantum circuits, you should get a primer in linear algebra. So a qubit can be represented as not can be not just the 0 or 1, but it can be a superposition of 0 and 1. So that is, you have a coefficient to 0 and a coefficient to 1. And this is also a can be represented as or thought of as a vector in a vector space. Okay. Uh, the difference between this and a vector that you can imagine 2D space is simply that alpha and beta here can be complex numbers rather than real numbers. Uh, in classical computing, you have uh, just to compare how to represent them. Zeros and ones are just two dots in space. Okay, just uh, that's it. You have a zero that's a dot and a one that's a dot, and there's nothing in between. In quantum computing, you can represent states here on this shell. That is anywhere on the surface of this sphere, and that's given by this superposition expression alpha 0 plus beta 1. And again, we don't have time to go into the math here, but we can represent this using these variables phi and theta as cos theta by 2 and e to the power I theta psi theta by 2. So this is a complex number, as you can see. The property that we want here is that we want, so I mentioned that when you measure a qubit, it collapses to either the 0 or the 1, right? The probability of its collapse to 0 is represented by the coefficient of that squared. That's the modulus of the complex number, and same for the state 1. The thing is that we represent qubits such that the because we want the probability of either 0 or the 1 to add to 1, so the sum of these has to be equal to 1. So that's what we call a normalized qubit. When you have the coefficient square, the modulus of the coefficient square, is added to 1. Moving from that to gates. So this is in classical computing, you can have we have what we call logic gates. So this is the simplest logical gate we can have. That's a NOT gate. In quantum computing, the equivalent of that is we also have a NOT gate. We call it the X gate or the poly X gate. In classical computing, we use Boolean algebra to reason about how a gate can convert an input to an output. So here in the gate, if we provide the input B is 0, the output is going to be 1. If the input is 1, output is 0. That's what a NOT is supposed to do. In quantum computing, we can't use Boolean algebra. We use linear algebra, which is an altogether more powerful computation method. So the state is represented by a 2D matrix. And when you provide the input Q, let's say the input Q is 0, and as I showed in the previous slide, that can be represented as this column matrix 1, 0. In effect, what this gate does is it's going to do a matrix multiplication on the input gate. So if you want to think about this in purely mathematical terms, what we're doing here is a matrix multiplication. Or in linear algebraic terms, that would be a linear transformation. And yeah, you can apply gates not just to a 0 or 1 state, but you can apply it to any superposition state. That is one with the coefficient of alpha or beta. What is the unique selling proposition of quantum computing, though? It's the ability to convert basis states, that is states 0 or 1, to superposition. And for that, we can actually build something and use something called a Hadamard gate. What does a Hadamard gate do? It can be represented by this particular matrix. If we apply a Hadamard gate to the state 0, we're going to be doing this matrix multiplication. This is something you might relate to. Just I think most of you probably know how to do matrix multiplications. What we end up here is we end up with, if you do the multiplication, you see this is what we end up with. We end up with the 0 state with the coefficient 1 over root 2, 1 state with the coefficient 1 over root 2. And if we do add the squares of them, we get half plus half equals 1. So this is an example of a normalized state. What does the state represent? This represents an equal superposition of a 0 and a 1. And that in real quantum algorithms turns out to be very, very useful. We also call this particular state a plus state. Same thing if we change if we apply the Hadamard gate to the state 1, we get what's called a minus state. So we can put a basis state or a 0, 1 state into superposition, but we can also do the reverse. We can convert a basis state or a superposition state back to a basis state by applying the Hadamard gate again. And when we apply two gates in succession, you can reason about it as you can effectively collapse this to one gate by just multiplying the two matrices. So we know what H represents is this matrix. It's multiplied with this matrix, and you get this. And if you know your matrices, you know that this is the identity matrix. So therefore, Q simply gets converted back to Q, right? All right. So I'm going to stop there, and I'm quickly going to pivot to the IBM quantum experience. And I think we have 7 minutes. Maybe we can just take 10 minutes, right, moderators? Just a couple of minutes more.
Yes,
And I
sir.
will.
We're going to have.
Sure. So this is what we call the IBM quantum experience, and this is open for anyone. Okay. If you just Google IBM quantum experience, this is basically the first link that you're going to get, quantumcomputing.ibm.com. And once you go here, I imagine most of you probably don't have an IBM ID, but you can get one for free. Just click on this link, create an IBM account, and you'll get an IBM ID. Okay. Now I have one, so I'm going to just log in. Right. So this is a bit slow. All right. So yeah, this is a little slow at this point, but let's see how fast what we can do with this. So you see the different features that you can get here. So what this offers you is the ability to do some basic widget-based programming, as well as it offers a lot of documentation. So I'm going to go over to the composer. So the composer allows us to build circuits by using a drag and drop method. Okay, so I'm going to click launch composer, and if you're going to be playing with this, do the same. Just experiment with the composer first, and then my recommendation would be to go to the Qiskit textbook and then read up on the basics there. Okay, let's wait for this to load. All right. So you saw me click this tab here, and now you get these composer docs and tutorials. Okay, so again, even beyond this session, you can go and create your own first circuit, explore. There's a lot of documentation here given that you can check out later. Okay, for now, I am going to just show you a couple of very simple circuits or gates really. So here we have, okay, let me take the simplest thing possible here. All right. So we have, you see two lines here. There's a line Q, which represents a qubit, and there's C1, which represents what we call a measurement output. So this is a classical, this is a qubit, and this represents a classical bit. Okay. What that means is that in our circuit, we can have a qubit as an input, and we can do some things with it. We can create some gates here, which I'll just show, and then you can, when you finally want to measure it, that measurement will be to this C1, that the classical bit. Okay. Now, I see, you see here, this is a NOT gate. Okay, so I'm going to drag this gate here. All right. What this does is it applies a NOT gate to Q. I just showed you the NOT gate on the slides, right? So here you see, so initially, by the way, by default, all inputs are supposed to be 0. So when we do a NOT, uh, let me just increase the size of this thing. Okay. So the output that we get here is really, it's kind of a probability distribution. So you're going to this shows you what is the probability of, because it's just a one qubit, right? So it can be and it can be in a superposition of 0 or 1. Here we see that because it was originally 0 and we applied a NOT gate, the output is 1. So probability of it being in 1 is 100% now, right? Let me apply another NOT gate here just to show you what's going on. And now you see, they go to refresh and see, from a 0 went to two knots, back to 0. Okay. I'm just going to delete this. Okay. And now this is the measurement symbol. Okay. I'm going to measure this. What this means is I now require, after passing Q through the NOT gate, I want to measure the output and have that reflected in my measurement. So this, again, we measure it because it was a state of it is 1. It's going to measure, it's going to give me just a 1. So any basis state, when you measure it, it's supposed to give you that state itself, right? uh, what do we have here, by the way? What we are doing here to do, what are you seeing, the output that you're seeing here, that's really being done via a simulator. So the simulator that's running when I drag and drop these, and that's producing these outputs. Now, what is I mentioned that these circuits that we're creating, they can be created through the SIESGST framework, right? The programming framework. You see here at the right, this is actually the code that represents this. Okay. Now, once you understand the basics, once you've played with this, and you go on, you can then actually go on to writing these programs directly rather than using this drag and drop method. And there is a, if you look at the, go to the qiskit.org website, you'll find out how to install the right tools to be able to start writing this code. But here, this just shows the code equivalent of the circuit. And you see, just show you a flavor. Think of the circuit as being just representing the whole circuit, and circuit.x means I applied a NOT gate. This operation is represented in this line of code. Okay, and then this measurement is represented in this line of code where you're saying circuit dot measure the qubit and record it to this classical bit. That's what it's doing here. Okay, now let us take another interesting gate. I just talked about this Hadamard gate, right? Okay. Sorry, this is a bit slow today. I think it's partly because of the streaming. All right, just opened a new one, and I'm going to do the same thing here. Okay, so now we have a qubit and we have measurement, a classical measurement. So now I'm going to apply this H gate, the Hadamard gate. Okay. Immediately you see in the code circuit.h. Last time we saw circuit.x, now it's circuit.h. So we applied a different gate to the our qubit here. What is the output? So the output here, as represented in the qubit, is it's in an equal probability of 0 and 1. 0 has the probability 50%, 1 has the probability 50%. Okay. By the way, this is we don't have time to go talk about Q spheres today, but you can see that's what is represented here. And again, if you try this out at home on a computer, you should be able to see that much faster than I can show you right now because my computer is rather overloaded. Let's do a quick measurement here, okay? So now we measured this. And now you see here, the qubit, when we just left it the qubit, because again this is a simulator, it can accurately measure or report what the output of qubit is. But when you're measuring something, it tends to collapse to a 0 or a 1, right? So at this point, the measurement has collapsed to a 0. Okay. And if you actually if you run this program multiple times, you see sometimes it'll show you 0, sometimes it'll show you 1. The idea of Hadamard gate is that if you run it enough times, 50% of the times you measure, you will get a 0, other 50% you will get a 1. Okay. Now, just to complete this process, check out this setup and run option at the top. What you can do here is, so far we've been just running this Qiskit program on right here using a simulator. But we can actually submit it as a job to a real IBM quantum computer. So one of the quantum computers that are actually free for use is called IBM Q Armonk, and it can support 1 qubit. Okay. So easiest way of again doing that is just, you see this option here, run on IBM Q Armonk. Just click on that. And you see it's running here. And you see job sent and it's pending. What does this mean, pending? It means that let's just click on that a bit. Yep. So this is because the IBM computers, they are open for use for everyone around the world. They get jobs, like I'm sending a job. A lot of other people at this point are sending a job from their computers, right? So my job is now in a queue. And as you can see here, that's what it says here. It's in queue, expected to run in 20 minutes. So we don't have 20 minutes right now, but 20 minutes later, I will see the output of this program here, and it will be something very similar to this, except it ran on an actual quantum computer rather than on my machine via simulator. I'm going to stop there. I hope this gave you a good preview of what IBM Quantum is, what's the value proposition that it brings. I hope it has piqued some interest in you to start learning a bit more about quantum computing basics, and then start being quantum programmers yourself. And hopefully, some of you may go on to do some great research in this area. So I'll stop there, and yeah, I'll also stop sharing my screen. Thanks everyone for listening, and we'll take any questions if you have any.
Thank you so much, sir, for that amazing session. I'm sure the audience will have been able to grasp great understanding from all the concepts that you covered today. So now I'd like everyone in the audience to post their comments and questions so that sir can answer them. So this question is from Ronit. He asks, how are qubits stable enough?
Yeah. So the short answer is depending on the time, they may not be. So all these technologies have something called coherence times, and all the various kinds of qubit technologies have more or less capacity to hold on to the state. So uh, the whole idea of running a quantum circuit is that you build, at least today, build a quantum circuit that is as short as possible, so that when you transform the states, they hold on to the states, and you get your output, you measure them, and up to that point, they are not going to uh, collapse. So we are not at the point, like say with classical computing, where you can indefinitely hold on to a state on a, let's say, like a solid state device. We are not there yet. We're heading there. Error corrections are probably the hottest topic in quantum computing, in core quantum computing research. But yeah, short answer is uh, with today's quantum computing technology, you should try and build small circuits to solve your problems. So there's a lot of interesting ways you can do that. But if you are depending on a quantum circuit to just hold your state indefinitely, you'll have to wait a few more years.
So next question is from Khush Patel. He asks, how can quantum computing with IBM help progress in communication space, 5G, and cybersecurity?
Next, yeah, a rather broad question. I think communication. There is some work on quantum computing. Yeah, that's an area called quantum internet. It's not something I'm super familiar with, but it's one thing with computing is this property of entanglement, where you can entangle two qubits. Like again, if a lot of your audience is familiar with physics, if you recently graduated from high school, you should probably know that. You have the notion of wave particle duality, right? And the idea that the particles can have both wave and particle and quantum properties. So with the thing is with any particle that has the quantum properties, you can apply certain gates to them, so that they end up being in entangled states. And then if you take those qubits far away from each other, you can it turns out that when you measure the two different qubits, they give you the same answer. So that's like what Einstein back in the 30s called spooky action at a distance. It's one of the unique and very interesting features of quantum computing, quantum mechanics really. But that kind of thing, the ability to be able to communicate uh, uh, information, is probably can be harnessed in communications. We don't have any technology for that right now, but people have actually experimented with entanglement. So watch out in the near future. I think you may get something there. Space. Probably it's the same category as a lot of the problems that I mentioned early on. The Like, we would like to be able to create more energy efficient solutions, or figure out logistical problems. All of these problems have the common characteristic that you have to reason over a very large number of states, which can blow up exponentially, and you want to be able to make quick decisions. So I can imagine when you're doing space, anything you want to do when it comes to space technology, like, and maybe communicate with the Mars rover, for example. There are things you may want to do a lot faster than it is done today. So again, this is not something I'm an expert in, speculating a bit, but this is the takeaway you should have: is that wherever you have problems that are today inherently slow, because classical computers cannot handle exponential problems fast, there you can potentially use quantum computers to speed up things. Um, Cybersecurity, there's a yeah. Let me just quickly answer that cybersecurity question before I go to the
Yes,
next
sir.
one. So there are people are doing research on cybersecurity. There are if you know some classical security techniques like public key encryption, there are um, uh, people have proposed algorithms whereby you can break public key cryptography using quantum computers. The thing is, though, the state of the quantum computers that we have today do not. So that, I mean, short answer is people don't need to worry about it at this point, because the state of the quantum computers today are not uh, uh, error free enough or high capacity enough to be able to do such encryption breakings. But there's a lot of interesting research that's going on in cybersecurity, and we can envision a lot of both when it comes to breaking as well as in strengthening systems. You should watch out for a lot of research. That's I think if you go to the if you check out IBM research papers or even blog articles, you should be able to find some good material on this. Okay.
Yes, sir. So the
Question.
next question is from Samiksha Rai. Is the concept of a
Just
user
before that,
interface?
sorry, I just missed that. There's a
Yeah,
question
it
about.
got skipped, sir.
Yeah.
So we can answer this and then we can move to that.
Okay.
Is the concept of a user interface or user experience relevant to quantum computing?
Not in the way you think of UX with respect to web pages today. I imagine that's where the question is coming from. You're thinking of how you can build user interfaces right on top of a quantum computer, just the way we build user interfaces that expose that does some sort of client server interaction today. Um, the user experience, again, user experience is a broader term than user interface. uh, I showed a few slides where I showed where we can program from our laptops. It goes that program then goes to a cloud. The cloud then does a transpilation of that program into a circuit. It's a synthesis. The circuit then gets converted into what are a sequence of microwave pulses which go to the actual quantum computer which resides in the backend, and the quantum computer then does that processing and comes back. Now, there are I alluded to this in one of the other slides in the takeaways that we should get from the in the takeaways from the roadmap. So the programming experience you would have had maybe until about a couple of months ago, that this is how you would do it. But right now, very recently, we've had some advances in how you can build quantum programs, whereby uh, you can write programs that ask the backend quantum computing for more customization, like do some if then else kind of thing, which it could not do earlier. So earlier, you would just submit a quantum computing program, it would do something, return back. You would maybe do the if then else in your using logic that's running on your laptop, send it back, and so on. But those are things that we can shorten right now, and that's the it's sort of a developer experience that has been we've been trying to improve recently. And so, yeah, definitely you should see some improvements there. I showed you that one slide where I remember I mentioned, say in 2023, you should have any domain expert. You should be just able to provide a data file saying, "This is my data. Solve this problem for me and tell me the answer." We want to actually go there. So that's the kind of user experience that would be very valuable from a programmer's perspective.
Yes, sir. Next question is from Madhuri Ramakrishnan. Can quantum computing provide the possibility to decrypt blockchain technology?
So I alluded to this earlier about so a lot of blockchain technology is based on public key encryption, and uh, yeah, from a theoretical perspective, people have proposed ways whereby you can break public key encryption. And why? Because and let me mention, I might have omitted to mention this earlier. If you think of how to multiply two numbers, multiplication of two numbers is very easy for a classical computer. In fact, we can do a lot of classical computers are measured on that basis. Like if you take flops, floating point operations per second, you can treat how many multiplications you can do as a benchmark for how good that computer is. Um, Multiplications are straightforward to do; they're fast. Take the reverse problem. You multiply two numbers, you have a product. You want to factorize it. That in mathematical terms is actually hard, and that difficulty is what public key encryption is actually based on. The fact that once I encrypt using public keys, only someone with a private key would be able to decrypt it because factorization is hard. Now, if factorization were easy, anyone could break that, right? So, what quantum computers promise to do is to make factorization easy. But so if we are at a stage where factorization actually becomes easy in practice, factorization of very large numbers, I'm talking about very large numbers, not talking about numbers like 6 or 10. The you're going to then at that point it may be practical to break it, but we are nowhere near that at this point. So there is a lot of research ongoing in this area, and just yeah, any breakthroughs in cyber security will also carry to blockchain.
Yes, sir. So the next question is from Biju, sir.
Yeah,
What
the
is the procedure
answer is
for
yes.
Yes, sir. What is
Answer
the
is yes.
procedure for public to access IBM quantum computer via the cloud? Is it through IBM login ID, like you have demonstrated?
Yeah, okay. It doesn't require an IBM login. So I have an IBM ID that I have an IBM.com address, so I use that. But if you go to the quantum-computing.ibm.com, you get an option to create an IBM ID, and anyone in the world can create an IBM ID. So just create that, log in, and use the tools that I previewed for you.
Yes, sir. Are there any more questions? Uh, okay. One more question from Abhishek Singh. What are the most common design patterns for algorithms for quantum computing?
Yeah, at this point, we don't have design patterns of the kind that I think you are asking about when it comes to like say you want to use map reduce kind of pattern, that we use in JavaScript or Python. We are not quite at that stage yet. You have to, if you're going to be programming quantum computers, you have to write reason about things at the circuit level at this point. So there, the design, yeah, we're not quite at a level where we can write programs at such a high level that we can then determine or settle on certain design patterns that most developers can use. So we are not quite there at this stage yet. For the patterns, how to build quantum circuits themselves, the benchmark there is simply at this point, how do you get uh, an output that is as error-free as possible, really? So the rule of thumb is to not build circuits that are too deep. So I showed you some examples of circuits where uh, you can have some gates followed by gates followed by gates, right? The total number of stages that you go, that's really referred to as the circuit depth, and the deeper the circuit is, as some of the questioners asked earlier, the longer the time it takes to go from input to output, and your circuit is not guaranteed to maintain its coherence for that long. So today, the a lot of the intelligence or the cleverness in writing a quantum program or quantum circuit comes in determining, okay, maybe my problem can be solved by a circuit of depth 10. How do I compress that to a depth 6 so that I can get a more accurate answer from the program?
Yes, sir. Mitesh is asking, does IBM Quantum have quantum annealers? I hope I
I
pronounced that
think
right.
we can probably implement it. Yeah, check out the Qiskit suite of tools. I'm not. They probably do have support for some quantum annealing tools. Uh, yeah. Otherwise, I think the yeah. Just to mention, the quantum annealing is sort of an alternative way of doing quantum computing, which this company called D-Wave has been propagating. So again, a lot of people in the quantum computing world believe that is not really quantum computing per se, but yeah, I think you can. There may be tools in Qiskit. So yeah, I don't know that off the top of my head, but if you look in the Qiskit suite, you should be able to find out. Go to qiskit.org, go to the textbook, yeah, go to the Qiskit library, and
Yes, sir. So this question is from Karthik Iyer. So, what is the implication of quantum computers in machine learning or even artificial intelligence?
Right. So I mentioned this in the category of broad category of problems that quantum computers have the potential to address. AI and ML being one of them. So just like how AI is used for a lot of mainly for if you want to abstract every problem into AI into one term, you can think of it as pattern recognition or feature detection, right? Quantum computers definitely that's one of the key areas that quantum computers have the potential to handle much faster because AI, as you know, in general, AI is all about handling exponential states, but using heuristics, right? So it's a different way of dealing with an exponential state space. Um, but with quantum computers, you can probably handle AI problems in a different way and get more accurate answers faster than you would with conventional AI methods. Similarly, for machine learning, you can train your models a lot faster than you would today with today's ML technologies. So that is the promise. Check out some of the uh, papers and articles. If you can Google IBM research, quantum machine learning, quantum AI, you'll get a lot of hits for that.
Yes, sir. Next question is again from Ronit. How are qubits stable enough to hold on to data over time?
I think we already talked about this, right? That they are
Uh,
the qubits. Uh, they have, yeah, at this point they are somewhat error prone, and qubits they have like any quantum particle, they have a coherence time. So which means that a qubit, when it is in superposition state, has the tendency to drift from that state. So that's it cannot hold on to that state for an indefinite amount of time. In the IBM quantum processors, as I mentioned, we use this technology called superconducting transmon qubits. Uh, these qubits, the way we get them to hold on to their state as long as possible is by cooling them down to very, very low temperatures. 50 millikelvin is the temperature that those qubits are held at this point. So, but besides that, to answer your question, how can they hold them over time? Short answer is you cannot indefinitely. It's not like storing state in a solid state device like storing data in an SSD drive like in do today. That's not what you can do with qubits.
yes, sir. Next question is from Devorsi Vasu. Is quantum cryptography already in the market? Can you please tell us some of its use cases?
Again, I don't have anything more to say beyond what I said just a few questions ago. It says this is still a topic that people are actively researching, and there is an IBM security team that is dedicated towards solving security problems on with quantum computing technology. Um, Theoretically, people have figured out that it's possible to break public key encryption, but in practice, that's not possible at this time. Not probably, maybe not going to be possible for some time to come. But keep tracking that. So yeah, already in the market. Answer is no, but people are working on it.
Okay, sir. So that was the end of the Q&A session. So now it's time to test the audience about what they all have learned. So a link for a quiz based on today's session will be provided in the comment section, that is the chat box of YouTube. Make sure you all attempt this quiz as it contains 10 questions of 3 points each, making it 30 points in total. Remember that there are exciting badges and prizes lined up for the top performers of this activity. So you should get the link soon.
Thanks, guys. Yeah, you're welcome. And great questions.
Thank you so much for attending the quiz, everyone. Hope you all learned a lot of new concepts today. So I think we have come to an end of this incredible session. Thank you, sir, for taking time out of your busy schedule and agreeing to be a part of Epsilon 2021 and enlightening the participants through this amazing seminar on quantum computing basics. We hope to have you with us again soon. We would also like to thank all the participants present here for being such a great audience. We hope to see you all again tomorrow for day 2 of Epsilon 2021. Thank you, everyone. Bye bye.
Thank you, everyone.